Hi, I'm Adam. I'll be doing a series of instructional videos on the Regional Hydrologic Extremes Assessment System, or RHEAS. Note that Rhea was a Greek goddess, the daughter of Gaia. Rhea also means to rise in Cambodia, where I work, so Pre'at Rhea is sunrise. Just a quick note before we begin, I'm not the developer. That would be Konstantinos Andreadis, or Kostas, at JPL, along with Narendra Das at JPL, who works on the agricultural modeling. I use it though and have been involved with the initial troubleshooting, so I'd like to pass on the knowledge that I've picked up, because I consider this quite a valuable tool. RHEAS's backend is a PostGIS database. It first fetches data automatically using user presets, then it runs through the Variable Infiltration Capacity, or VIC, model, a macroscale soil moisture model, and uses ensemble-Kalman filtering to forecast. This is similar to Monte Carlo simulations using Bayesian methods. That's the hydrological end, and from there the soil moisture can be used as inputs for the DSAT, the agricultural component of the model. I'll get into all of that later, along with the installation and straight-ahead tutorials. But first, we'll touch upon the inputs, starting with something slightly important for a soil moisture model, which is precipitation. There may be more data sets added. We don't know yet. If there are, I'll update this video. But these are what we have right now. And knowledge a lot of these is not an absolute requirement for running the model. But what if, for example, you're in the position to choose which one is best? It's nice to make an informed decision. So here's a list of possible precipitation inputs. I'll be discussing RFE2 last because it's regional and only pertains to Africa. Note that spatial resolutions are sometimes stated in kilometers, where 1 degree is 100 kilometers. This is because the circumference of the Earth divided by 360 degrees maybe roughly equals that when we're here working with RHEAS shortly north of the equator. However, I studied in Canada where lines of longitude are only half the distance between one another. So, I prefer to stay away from that equivocation, but it is nice to remember because it is hard sometimes to try to picture a resolution of 0.25 degrees in your head. So just remember it's around 25 kilometers near the equator. Of course, it wouldn't be around the Antarctic Ocean, but well, you probably know the outputs for soil moisture and crop yield anyway, if you're down there. So here we got CMORPH, CHIRPS, TRIM, GPM. TRIM and GPM are related. So I'll be covering those together. And RFE2. If you need links to any references, initial papers, or anything, they're provided in the description. So we'll start with CMORPH. 0.25 degree resolution from 60 degrees south to 60 degrees north. Starts at 23rd of February 2005 to, today is the 4th of April, and it was last updated on the 2nd, so it's quite recent. One of the reasons I really like this data set. Apparently, they're working on reaching back to 2000s, but there's a gap in the data somewhere in 2002, unfortunately. We're getting this from the IRI data library. That's the International Research Institute for Climate and Society at Columbia. You'll be hearing about them a lot. It's produced by the Climate Prediction Center, or CPC, of NOAA's NCEP. That's the National Centers for Environmental Prediction. The temporal resolution is actually quite high at 30 minutes, which is much higher than we need, in fact, so we just use the daily files, which are sometimes called the daily sums, sometimes called the daily means. Anyway, first described by Joyce et al. In 2004, it's CMORPH, a method that produces global precipitation estimates from passive microwave and infrared data at high spatial and temporal resolution. That's most of what you need to know right there in the title. Importantly, it exclusively uses satellite data. First, precipitation is estimated for 4 satellite systems and their algorithms. This starts with the low orbiting passive microwave observations. Let's skip the algorithms. This is TRMM, TMI rainfall, ACWA, AMSRE rainfall, DMSP 13, 14, 15 SSMI rainfall, and NOAA 15, 16, 17 AMSUB rainfall. Of course, these satellites aren't everywhere all the time. Remember, the temporal resolution is quite high for CMORPH. So what do? They take the data from there and then they spatially propagate it and time weigh it using geostationary infrared satellite data. So they go from the microwave to infrared. Here, this is called morphing. The geostationary satellites are GOES 12 East, GOES 10 West, GOES 9 GMS, Meteosat 7, and Meteosat 5. The major strength of CMORPH, aside from its temporal resolution, which doesn't apply to us, is its standardization across the globe due to its not using any MET stations, and the benefit of passive microwave. For weaknesses, it's only estimating what's occurring between the swaths. And there are precipitation events that the infrared sensors can't pick up that we will miss, since, of course, there's no perfect correlation between cloud cover and precipitation. Next is CHIRPS. CHIRPS we're also getting from IRI. Its initial source is UC Santa Barbara, and it's a project done by USGS, funded initially by USAID, NASA, and NOAA. It's quite new, the latest version is only introduced in 2014 by Funk et al., but it dates back in time to 1981, so along with NCEP as a MET forcing file, which we'll get into in the next video, it will be quite useful for forecasts. Unfortunately, the latest at the moment, as I speak in April 2016, the latest data that we're using is December 31st, 2015, which was disheartening after I downloaded it all. From the literature, it looks like availability is increasing, and we're currently fetching a final product for accuracy. But for something like nowcasts and hindcasts, and hopefully forecasts in the future, this is perfect. It's 0.05 degrees resolution from 50 degrees south to 50 degrees north. There are two parts of the CHIRPS process. First, from satellite infrared precipitation data, they measure 5-day intervals, or called pentads in climatology, 5-day intervals, where the cloud top temperature is below 235 degrees Kelvin, and using already known regression methods from TRMM 3B42, they give the pentad a percentage of precipitation compared with the long-term mean. They then multiply this by the CHP climb, which is called the Climate Hazards Group Precipitation in Climatology. This uses a moving window regressions and inverse distance weighting. You multiply it by the CHPC climb pentad to make a gridded estimate of precipitation in millimeters spatially, called the CHIRP. They then use stations to correct this data, ground stations accounting for example, orographic features. Where the stations exist, of course, when there's a lack of density, what can you do? CHIRPS is quite the feat, though, when you consider the variable levels of data preparation at MET stations across the globe. Very valuable data set. Next is TRMM. Please note that TRMM actually wrapped up operations in 2015 and was replaced with GPM. So I'm covering these together more or less. It's a joint operation between NASA and JAXA, which is the Japanese Space Agency, and it ran for 17 years. Apparently, GPM algorithms are currently and will be run on past TRMM data, but until then, TRMM remains useful until that's finished. It stands for the Tropical Rainfall Measuring Mission, and the data we're using, product 3B42, has a resolution of 0.25 degrees between 50 degrees north and south latitudes. So to produce this data set, first they take data from two sensors on board the TRMM satellite itself. These are the TMI TRMM microwave imager, which is a passive microwave sensor, measures rainfall intensity, water in clouds, and water vapor. and the VIRS, visible and infrared scanner. You know if that's VIRS or VIRS, or if you're not a fan of the RHEAS, I guess it's VIRS. That just measures the irradiance in 5 bands from 0.63 to 12 micrometers. And it's mainly used to calibrate data coming from the other satellites, which all measure infrared. This is the monthly calibration parameter. TRMM also contains sensors to measure lightning and radiated energy from clouds and the Earth's surface. But here we're only interested in rainfall. So anyway, it uses this data to calibrate the infrared data from the GMS, GOES-E, GOES-W, Meteosat 7, Meteosat 5, and NOAA 12. I'm sure it's becoming clear that using microwave imagery to calibrate infrared is a common thread throughout these data sets. A lot of the difference is the calibration methods and the amount of inputs, and then whether it goes on to include surface station data. So note that this is only called the tropical rainfall measuring mission. I live in the tropics, and while when it rains here it generally pours, TRMM was never that great at measuring light rain or snowfall. And even snowfall matters here in the Mekong due to the river's origins in Tibet. So GPM is meant to rectify this. That has a spatial extent from 65, so it's gone from 50 to 65 degrees north to south. And specifically, we're using data that, again, is collected not just by GPM, but by a constellation of satellites. The final process is called the Integrated Multi-Satellite Retrievals for GPM, which is a backronym if I've ever heard one. It's iMERGE. iMERGE, again, calibrates and then merges and interpolates from microwave sensors, infrared, and now it includes gauges on the surface. So first, for calibration upon the GPM satellite, it again has a radiometer, but this measures 13 bands. And it also has a dual frequency radar, the only one in space that we know of. And this can measure precipitation in three dimensions. Pretty cool images it produces. But we use it for calibration. So GPM is also just the core satellite of a constellation. Like I said, it's calibrating all the data from the others. This video does not show all the satellites involved in the iMERGE inputs. It takes first the low Earth orbit satellite for thick passive microwave, and it morphs that data through linear interpolation. Then it's using the technique developed for CMORPH for the infrared sensors carried on geosynchronous satellites. I won't list them all because they're a very, very large amounts, but they're pulling data similar to how we are from many sources, and this changes due to availability. And then lastly, GPM uses precipitation gauges for further fine-tuning, about 16,000 of them. Hopefully someone will make a video of all that one day, but as it stands, that would crash whatever video processing tools you have, unless you're using some advanced dark editing software that we don't know of. Yes, a lot of the ingenuity between iMERGE is, in fact, how it can deal with drop data sources. But again, yes, it's an absolute improvement upon TRMM. So if you have a choice, just use GPM. Lastly is RFE 2.0. This is the African rainfall estimate, which is why I saved it for last. Resolution is 0.1 degrees, and it has a spatial extent of 40 degrees south to north, and 20 degrees west to 55 degrees east. Just a point on the spatial resolution of these data sets. Before we go further, remember that VIC, the variable infiltration capacity model, into which these are placed, is a macro scale model. So even if you've got 0.01 degree data for both precip and met, and also for soil, which we do have a good resolution for, VIC can't really handle that. It's the cold hard truth. And VIC is the best model out there for soil moisture and runoff models. So once we reach 0.25 degrees, what we're really looking for is accuracy. RFE, anyway, back to RFE 2.0. It uses 3 satellite estimates that are combined linearly using weighting coefficients, which are ground truthed with rain data up to 1,000 gauges across the continent. Satellite data uses passive and active microwave data, and cloud top infrared. So it's pretty similar to what you've seen already, just a different algorithm, giving you another choice for this part of the world. Okay, so I hope that was useful. In the next video, we'll discuss the meteorological inputs, which are NSAP and MERA, along with the standard VIC input files, which are global soil type and vegetation parameters. See you then. Thanks for listening.